All right. How's the sound? How many people do we have here? 89 is on the list. "52 is in the classroom." Assuming only people who are in the classroom entering WebAssign, it's available. Well, please, again, answer the same question. So please just go to the WebAssign. All questions which you see on the screen, you can see on a WebAssign. So you don't have to see these questions. And oops. Well, the average for this exam, the average grade was about 30, which is lower than the grade for the first exam, which is happening every single year. And I don't have an explanation for that, because it doesn't mean absolutely not everybody did worse. No, actually, some students did better, some students did much better than on the first exam, from 20-something to 30-something. So there are three groups of students. Students with improved grade, students with almost the same grade, and students whose grade dropped. And again, I cannot explain why would that happen, and no one can. There is no science of education. It doesn't exist. It's something psychological. But I read all your feedback. You can read them on Blackboard. And for example, a student writes that he or she, I don't know, started watching lectures and it helped. Well, that's a specific piece of information which might be useful for everyone. Some feedback wasn't really specific, like, I'm stressed, you know. Yeah, we all are, so. Some students, again, said good or bad things about teaching fellows. We'll pass that information on, but without information about the lab section, it's really hard to figure out what to do about this. You know? So when you leave with feedback, the more specific it is, the more helpful it is. If it's just a ventilation of emotions, that's good, but it just doesn't provide information workable for the future, you know. Now, the good news that, again, historically, the last exam average is always closer to the first exam average. It's just fact that, like, you know, in the morning the sun comes up and in the evening the sun goes down. No one knows why. The amount of material, the level of difficulty of this course is defined by its title, Elementary Physics, PY105. Summer course, as you know, is more intense. It requires everyday attention. And I'm asking everybody who is satisfied with the grade, go to Piazza. You don't have to write your name, or you could, you know, to brag about what did you do to get better prepared, and other students would benefit from that. And 2 weeks ago, I mentioned the fact that historically, students find exam 2 harder than exam 1. Yes, it happened again. And I tried to explain that my hypothesis is because physics is, well, in a way, accumulative. The new knowledge is based on the old knowledge. If the old knowledge is shaky, the new knowledge might have some gaps. And to patch up those gaps. Again, some time and effort might be needed. And I expect now the distribution will be different from the distribution for the exam number 1, but similar to the last year. Last year, the average was actually a little bit higher, I think, 32 or 33, but no one got 40 out of 40. This time, 3 or 4 students got 40 out of 40. So the distribution changes every year and in an unpredictable manner. It's very common, to see the distribution like this. Actually, I would expect more people say that it was harder, not 31, well, out of 62. Some people don't participate. Well, anyway, that's another possible reason that the grade is not as satisfactory as some might wish. I firmly believe lectures and labs are important, beneficial. Otherwise, why bother at all? And one student, I said, wrote that he or she started watching lectures and it helped, so that confirms my belief. And students who don't participate, or students who are here and don't participate, they're missing out. This is what we started to learn, simple harmonic motion. And the first several slides represent just copy from the last lecture. Again, I never recommend stick to the deadline. This type of a course requires everyday attention. And we talk about simple harmonic motion, which is a type of a periodic motion. For a periodic motion to happen, a system should have a stable equilibrium. If we deflect the system from stable equilibrium, it should go back to that equilibrium by a certain force, a restoring force, the force which wants to restore that equilibrium. The easiest model to keep in mind is an object attached to a spring. However, technically, it's very difficult to find one spring who equally good at compressing and extending. So that's why instead we use a model with 2 springs. But in our mind, we can always imagine there's only one spring attached to this cart. And we did this kind of a calculation. The most important conclusion is for this type of motion, the equation which relates the instantaneous position of an object and acceleration is linear. Acceleration depends on position. This equation assumes that the origin, x equals 0, is chosen at the equilibrium. Doesn't have to be that way. We can choose it anywhere, but it's much easier to choose it at the equilibrium. And specifically for a cart or an object attached to a spring, we can have an additional equation which relates the mass of this object, the property of the spring constant, and this variable is related to the period. So again, it's very important to just know the definition of all important variables. For example, a period, time for one whole oscillation. When we talked about revolution, a period was time for one whole revolution. And we use an analogy between rotational motion or circular motion and oscillations to derive an equation, the motion equation for the instantaneous position of an oscillating object. We just have to look at how the x-coordinate of the circling ball changes in time. That's it. So the motion equation looks like this. Although, again, to remind you, when we talk about oscillations, we use different letter. We don't use R, because R forces us to think about radius. No, we use A. Mathematically exactly the same thing, but now it means something more relevant. A represents the maximum displacement from the equilibrium. So that's equilibrium. I can displace it by 1 centimeter, by 10 centimeters. And if it's displaced by 10 centimeters and released, and we don't touch it anymore, it can't go any further than 10. So that will be the maximum displacement. That's what we call the amplitude. And if you remember trigonometry, cosine or sine functions have a limit. It changes between 1 and -1. So you can plug any numbers in this expression. This whole expression inside parentheses has a name, a phase. Yeah, everybody has its phase. This is the phase of the oscillation. And you can use degrees, you can use radians, no matter what you use. If you take a calculator, calculate cosine, all values will be between -1 and 1. And if you're multiplying by a fixed constant, that means for this variable x, all values will be between -a and +a. That's it. And we will see some graphs like that. And this is that very omega. We call it now angular frequency, but we derived it from angular velocity. We just changed the name now. And time is a running variable. And this number depends on actual initial location. We don't have to worry about it. We will figure out how to get rid of it eventually. This is how a period and angular frequency are related. And there was a slide with those relationships. All right, now please take a calculator and calculate 3 numbers. Just calculate 3 numbers, but pay attention to the mode of your calculator, because your calculator has actually 3 modes: degrees, radians, and special degrees. So normally, if you reset your calculator, it automatically set to degrees. However, what people sometimes forget, the motion equation, x equals a cosine, usually requires using radians. So in these examples, you have to use degrees, so probably your calculator is automatically set to the right mode. If you're able to turn it on, I can't. All right. Yes. Oh, no. Hey, this slide is bright enough. So cosine, you don't see it, but I see at the top of my screen on my calculator DEG, so I know degrees. Cosine 35 equals, what do we have? 0.819. Okay. This number has no unit, it's just a number, right? Well, next number, negative cosine 35 plus 180. 0.819. Thank you. Next number, sine of 35 plus 90. Well, by now, our pattern recognition device, which we call a brain, should tell us it should be the same number, and it is. So what does this simple calculation tell us? It tells that technically there is no difference between cosine or negative cosine, or cosine or sine. We can always convert any function into any other function. The result will be the same. So this number, which is inside, doesn't really matter. We can get rid of it by switching from one function to another function. And you don't have to remember these conversions because they're available. The point is, to describe a simple harmonic motion, we can use any trigonometrical function: cosine, negative cosine, sine, negative sine. It doesn't matter. We can always go back and forth. So this tells us that in general, the motion equation for an object oscillating has this structure: a certain coefficient, a certain function. Then in parentheses, we have another combination, a number times time, a running variable, plus another possible function, plus in general, one more number, one more constant. So in general, it might have 1, 2, 3, 4 constants, one function, and one variable. Here, you can see many different examples which describe some simple harmonic motion. All have exactly the same structure. And of course, we know in mathematics 2 plus 5 equals 5 plus 2. So in general, you can rearrange the numbers in a certain way. It doesn't change the fact that this calculation still is, this equation still is an equation for a simple harmonic motion. It doesn't matter if the constant is the last term or the first term of the equation. Well, please tell me, if you look at this list of equations, how many cannot represent the motion, the simple harmonic motion? So the answer is the number. How many? Not which, yeah? But if you count, okay, I have counted 7 equations which cannot represent simple harmonic motion. You enter 7. And this is, again, an example of how our brain recognizes patterns. We already know what structure should an equation have. And now our brain starts making a comparison between a specific equation and a general structure. If it fits, that equation works for simple harmonic motion. If it doesn't fit, so that equation should be counted as the wrong one. I'm going to start collecting. Oops. And I'm going to switch back for a moment. So what about the equation number 1? Should we count it as the one which cannot be used? No, because it can. Number 2 can. Yeah, it has a coefficient, a cosine, and a phase. Can. What about this one? Cannot. It is missing a function. Can. What about this one? Cannot. It has a wrong function. Can. So two equations cannot be used to describe a simple harmonic motion. That's it. That's how it works. Well, so we saw this expression. We got it from an analogy between circular motion and oscillational motion. This is what we call a motion equation. Yeah? It describes the position as a function of time in general when the origin is not located at the equilibrium. And now we can erase from our memory anything related to rotation or circular motion. Now we can just use this as a fact. This is a motion equation for any simple harmonic motion. What is the difference between a simple harmonic motion and a periodic motion? Well, periodic motion doesn't have to obey cosine or sine law. It could be more complicated. For example, cosine plus sine still will be periodic. But a simple harmonic motion is described by a single function, cosine or sine function. And if we can, which is almost always, select the origin at the equilibrium, in that case, we set that constant to 0, and our equation becomes very, very simple. And in the future, we even will be able to eliminate this constant. So this is the summary, what we need to remember. A definition of the amplitude, a period, frequency, angular frequency. And these are definitions which can be used for any type of a simple harmonic motion, including a ball on a string, a vertical spring. But if we have an object attached to a horizontal spring, we can add one more equation. Now we can start thinking mathematically. Well, first of all, this is the motion equation. How would we plot the graph? Well, we have two options, of course. Number one, we can calculate several values for different values of time, calculate different value of x, and then plot it. But what we know is a standard simple graph of cosine should look like this. Cosine of 0 is 0, so it starts from 1. Then cosine goes to 0, and it happens at pi over 2 radians, or 90 degrees. And then it becomes negative, reaches another limit, -1, and then it goes back to 0, and then it goes back to 1. And this completes one period of a cosine. It ends at 2 pi radians, or 360 degrees. That's it. What is happening to this graph when we start using some additional constants? Well, for example, what does number e do to it? It means we have to add to each point of this graph the same constant, so it shifts the graph up or down if it's negative. What is happening to the graph if we multiply everything by a number, by a? Let's say we multiply it by 2. It stretches the graph in both directions, up and down. So instead of being limited by 1 and -1, it will be limited by a and -a with a possible shift. What is happening if we multiply time by a certain constant? It changes the period. It might be stretched, it might be squeezed. So in general, the graph looks like this. So it could have been shifted, stretched, squeezed. But still, it goes up and down, up and down. So this is the maximum reached on one side. This is the maximum reached on another side. Equilibrium is a position which is right in the middle. So equilibrium should be here somewhere, E. And this will be E plus A, and this will be E minus A. Those are limits. And the easiest way to see the period is to pick two adjacent peaks, for example. That this will be one period. It will not be equal to 2 pi, but what we know is, all right, I'll write it like we had it on a previous screen. It will be equal to 2 pi over omega, over that number, over that coefficient. If this coefficient is 1, the period will be 2 pi radians. This is a frequency, angular frequency. It tells how many oscillations happening in 2 pi seconds. So if this number goes larger and larger and larger, that makes period shorter and shorter and shorter. So it will be oscillating faster. It will be reaching the same position faster than before. That's it. That, by the way, is a good exercise to play at home. You can find online many free graphic calculators and play with the equation, plugging in different constants and see how it affects the graph. Question: if you look at this graph, what do you think is the period of the motion of an object described by this graph? First of all, do you see the exact period, the whole period? No, it's only a portion of that. But in order to find the whole period, we don't need to see the whole period. How many halves does a period have? Exactly. How many quarters does a period have? That's why we call them quarters. So if you see a quarter of a period, multiply it by 4, that will give you a period. If you see a half of a period, multiply it by 2, that will give you a period. What do you see here? A quarter? A half? 3 quarters, exactly. That's it. That's how we read the graph. So for any simple harmonic motion, the time to go from maximum displacement to equilibrium always equals a quarter of a period. From equilibrium to another maximum, another quarter. From maximum to another equilibrium, to another time when it reaches equilibrium location, another quarter. So what we see here is that a quarter of a period is equal to 2 seconds, right? 2 seconds, which makes the whole period is equal to 8 seconds. What is the amplitude? The maximum displacement from the equilibrium equal to. Do you read this number? No, but you can read this number. Still maximum displacement. So the amplitude will be equal to 6, because the amplitude is always positive. Well, what else can we calculate? Angular frequency, which is 2 pi over a period, or pi over 4 radians per second. Now, can we write the motion equation? Yes. So a general motion equation looks like this. But the equilibrium is a middle point between two amplitudes, and the middle point here is at 0, so 0. This number is 6. This number is pi over 4. This number is what we need to figure out, called the initial phase. So how can we figure it out? Well, we can use any value provided by the graph. For example, if I look at this graph, at this point, I can see that at t equals 0, x equals what number? 6. So I can use this fact. X should be equal to 6 when time is equal to 0. Which means 6 over 6 is 1. Pi over 4 times 0 is 0. 0 plus that unknown theta 0 is 0. So technically, this is the equation we need to solve. Cosine of something equals 1. Well, now we have two options. We may have the answer in the memory, or we can use a calculator and calculate the inverse cosine of 1. Well, my memory tells me cosine of 0 equals 1. So this variable will be equal to 0, which is consistent with the graph. This has to be a cosine, a pure, clean cosine, without any additional phases inside. So theta equals 1. And our final motion equation, I'll try to fit it, x equals 6 cosine pi over 4 times time. You can take a graph calculator, plot this graph. You will see the whole cosine. It goes infinitely, well, technically in both directions. But in physics, time starts from 0 and goes to the positive values, so we don't draw negative time. Well, one more question. If we know that the mass of the object attached to a spring is equal to 100 grams, which we have to convert into kilograms, what will be the spring constant? Well, mass and spring constant are related, but that relationship also involves another variable, the angular frequency. And we just have it found. So this is a standard definition. No, I don't want to take a square root yet. A standard definition of the angular frequency. What does it mean, actually? Well, what happened to frequency if we make a spring stronger and stronger? Well, for example, by cutting it. When the spring constant increases, this variable increases, so it's going to move faster. It makes more oscillations per second. The period shrinks. But if we increase the mass, it's heavier and heavier. In that case, what should happen to the period? The period should increase. It should take more time to come back to initial location. So the frequency should decrease. This is the oscillation with the 250 gram cart. Now I'm adding another 250 grams. You can see it takes more time to make one oscillation. So it's going to make less oscillations per second. So that's what it physically means. But we can use this equation now to calculate that spring constant. K should be equal to mass times angular frequency squared. Mass equals 0.1 and angular frequency pi over 4. And we have to square it. So 0.1 times pi squared over 16. And that's going to be a Newton over a meter. That's a pretty weak spring. Pi squared is close to 10. 0.1 times 10 is 1. 1 over 16. Small number. Someone should tell me the answer. I already have 0 in a point. Hmm? 0.6. Why not? Thank you. That is an additional information which can be extracted. Any questions? Well, so we're going to talk more about specific graphs now for this special case. Again, this special case describes the motion which happened like that. First, we set the origin at the equilibrium. So 0 begins here. Second, we moved the object away from the equilibrium. And third, we let it go from rest. So that automatically makes the function cosine or negative cosine. It depends on the initial location. So if this is 0, 0, 1, 2, 3, 4, well, 0 is at this middle point, so 10. My amplitude will be equal to 10 centimeters. That's it. And in a quarter of a period, it will travel through the origin again. In another quarter of a period, it will reach the opposite amplitude. Another quarter again at the equilibrium. And final quarter back to initial location. 1 period, 4 quarters. From here to here, from positive amplitude to negative amplitude, a half of a period. That's it. So this helps us to draw the motion diagram. And remember, the motion diagram describes locations. So well, I'm going to enlarge the picture. 0, the initial location, it's here, then it's here, then it's here, then it's here, and it is traveling faster and faster through the first quarter of a period. But then it starts slowing down, and it stops at the negative amplitude. And of course, then it goes again through the same locations, back and forth, back and forth. But the motion diagram now helps to figure out what is happening to velocity. How does, well, first of all, the initial velocity is 0, but in a fraction of a second, when the object is slightly to the left, to the initial location, how does velocity point? Left. It points like this. And then it points even more. And at the equilibrium velocity, which is maximum value, it speeds up, reach the maximum speed, and then it starts slowing down, slower, slower, and 0 again. Then velocity changes the direction, and the velocity points like this, faster, even faster, again reaches maximum speed, and then starts slowing down, 0. And now we can use this information to plot the graph for velocity. Well, the graph for position, of course, as we know, is just a pure cosine. Amplitude, 0, negative amplitude, 0, amplitude again. But what is happening to velocity? Well, first of all, it starts from 0. But in next moment, it's negative because it points to the left. See? The red arrow. So it points to the left. It's negative, and it reaches a certain maximum. Then the object starts slowing down, stops momentarily. This is happening. This is a quarter of a period, a half of a period. This is happening in a half of a period. This is a half of a period. This is a quarter of a period. But then velocity becomes positive. It starts pointing to the right, reaches another maximum, and goes back to zero. This graph represents one period of velocity. Is it a cosine? No. It's actually a sine. It's not just a sine, a negative sign. So for velocity, the equation looks like and people call it maximum velocity, but people call it also amplitude of velocity times negative sine omega t. Now, for velocity, omega different or the same? Same. It's the same period. It takes the same time to change. So this is exactly the same omega, exactly the same angular frequency. They have exactly the same period. And it's important to be able to sketch a graph like that. All right, what's next? Acceleration, of course. For the acceleration, the easiest way is to remember that we actually have derived the relationship between the acceleration and the x-coordinate. So if the graph for position as a function of time looks like this, looks like a cosine, what do we have to do to get the graph for acceleration? Flip it, because you're multiplying by a negative constant. So with the same period, how do we understand this? Newton's second law. F equals m times x. And the same force equals negative k times, I said F equals m times a, ax. M times a. And the same force is equal to negative k times x, negative spring constant times x. And if we look at the system, right now, there is no force acting on it, zero. If I stretch the spring, the longer elongation is, the stronger the force. But how does it point? Now it points to the left. At the equilibrium, force is zero. Here, the force reaches again maximum value, but points to the right, so it becomes positive. So the graph for the force, the graph for the acceleration looks alike. So this equation tells us to get the graph for the force, we have to take the graph for acceleration and multiply it by a positive number. So we kind of just stretch it a little. Second equation tells us to get the graph for the force, we can take the graph for the x-coordinate and multiply by a negative number. Well, so pictures show the graphs for this special case. And so acceleration as we know, for the sake of accuracy, I have to write that subscript because it demonstrates that I'm calculating the x component of the acceleration. It changes. Sometimes it's positive, sometimes it's negative. So acceleration reaches maximum when coordinate reaches its maximum. So in this situation, all we have to do is just multiply two numbers, 6 for the amplitude, and the angular frequency has been found. And that should be meters per second squared because it's an acceleration. Now, the expression for the maximum speed will be proved later using law of conservation of energy. And we will prove that the maximum speed, that what we also call amplitude of velocity, should be equal to just product angular frequency times amplitude of position, or just amplitude. So pi over 4 times 6. And that's going to be meters per second. And again, it's important that we got that information from graphs. Well, from this graph in particular. In general, of course, now I know that's a wrong file. Because, I don't know. Because I made changes on this slide. I know, remember that. I've added a couple of more equations here. That's why I couldn't see the average grade. Well, things happen. But the equations which I added here just sorry, can't do that. Is an equation which relates the force and position. Now I have to restart. Now it froze. Oh, technologies, designers. So the first equation and the second equation again for the acceleration. The same equation I had on the previous slide. Just give me a This is why I hate people who design these things. After every update, every electronic device works slower than before. They do it on purpose to push us to buy new and new and new. And if you think it's a pessimistic view, no, it's a realistic view. And sometimes I really wish that no Russian-speaking students would be present. But that's just a wishful thinking. We cannot rely on our wishes. We only can rely on science. So, second equation, which was here, represents a relationship between acceleration and the position. That's it. But I do remember I had it. So, the only one addition is this variable, and in this situation, actually, the equations should be related to the difference between the actual position and the equilibrium coordinate. Yes. That's it. And again, it's very uncommon. We would have to deal with something like that. Maybe one problem. Maybe this problem. So please tell me what you think about angular frequency for the simple harmonic motion described by that specific motion equation. What you see is two equations. One is general equation for any simple harmonic motion. And second is a specific, which describes the motion of an object maybe attached to a spring, and it actually starts from zero. No, not from zero. It starts from something. Well, so in general, what can we do? We can deflect an object from equilibrium, and also, when released, we can supply some initial speed. In that case, we can have an equation like this. But we don't have to think about the whole equation. When we need to find information about a specific variable, we just have to look at that specific variable. And that specific variable is something between what? Between time and the function. So wherever you see between the time and the function, that's omega. So the answer is 3 times pi radians per second. We also can immediately say that the amplitude should be equal to the magnitude. Well, I don't have to use bars here, but it should be equal to the magnitude of the coefficient in front of the function, which is 5. And these are all the two numbers which we need to know. We don't have to bother about other two numbers, because we can always eliminate those numbers by shifting our view or the origin, or when we start the time, when we start the stopwatch. So what would be the period of this motion? Well, the period of this motion is equal to 2 pi over omega, 2 pi over 3 pi, 2/3 of a second. And now we can calculate frequency. Frequency is 1 over a period, 3 over 2, or 1.5, 1 over a second, which is the same as 1.5 second to the negative first, which is the same as 1.5 Hz hertz. And again, maximum acceleration equals omega squared times a, 3 pi squared times 5. Maximum speed equals omega a, 3 times pi times 5. Oops. Where is it? That's a wrong file. Yesterday, 9:39. That should be this file. Okay, I have to... happen? No. I need my second computer. I'll be back in a minute. All right, so for this equation, please sketch the graphs. For position, velocity, acceleration, and force as a function of time, and calculate period, angular frequency, maximum speed, and maximum acceleration, and maximum force, and the spring constant, and assume that the attached weight has mass of equal to 100 grams. My computer is just right there, so I'll be back in a minute. You can ask me questions. If you ask loud enough, I can hear you. This is what happens if you use multiple cloud storages like I do. I have like 5 of them. So let's finish this, and let's do first graph. All other graphs can be extracted very easily because we know the procedure. So here, first of all, this is the trickiest part. What should we do about it? Well, first, we should draw a graph for a situation when it wouldn't exist. It would be 0. That function would look like this: 7 times cosine pi over 4 times time. That would have been just pure cosine like this. Starts from 7, reaches -7, and the angular frequency of this oscillation is equal to pi over 4, that very number between time and function. So a period, which is 2 pi over omega, would be equal to 2 pi over 4, pi and pi cancels, 2 over 1/4 is 8. 8 seconds. Okay. And now what we do? Now we have to shift this graph. Do we have to shift it up or down? No, because technically this is plus 0. The equilibrium is at the origin, or you can say the origin at the equilibrium. So this variable shifts the graph to the left or to the right. And we just have to choose the direction. And the direction says, well, the rule says, if it's a minus, it shifts the graph to the left. That's it. So the actual graph will look like this. Well, the easiest way, just calculate the value at t equals 0. X, the actual, yeah, this is no pi over 4. Yeah. The actual x at t equals 0 will be equal to 7 times cosine pi over 4 times 0 minus pi over 4. So you have to take a calculator to calculate cosine of pi over 4. Pi over 4 is a 45 degrees angle, and cosine 45 is square root of 2 over 2. So it's slightly less than 7, which is, so on original graph, this is this point, and now this point comes to the 0 time. So the whole graph just shifted to the left by this amount. So the actual graph will look, well, it's not easy to draw the exact same line, but will look something like this. And of course, with all equations we've learned before, we can calculate all other variables using exactly the same expressions. First, I want to show you what I meant to show you, the distribution, and to remind you again that all elements of the course are important. Crunching just homework problems is not enough. And now we can go through all these slides. And now this slide with equations, this slide with equations. So we have solved this problem, and now, so we are here. So we have talked about the special case number 1. Special case number 1, when object was released from rest, from a location away from equilibrium. In that case, the motion equation is described by a cosine. A special case number 2 is a case when an object was initially at the equilibrium, and then we gave it a push, one single push, like this. So initial x has to be equal to 0, but now the initial speed is not be equal to 0 because we made it not equal to 0. And in this situation, of course, we can repeat the reasoning we used for the special case number 1. We can start from a motion diagram. The motion diagram, again, is a set of photographs put together. So the origin and equilibrium are located at the same place. And let's say we gave it a push to the right. So the initial speed points to the right. But what is happening to the object? It's slowing down, and eventually it stops. Where? Well, that's the maximum displacement from equilibrium. It doesn't go any further. So that's going to be the amplitude. What is happening there? It reverses the direction, and it starts traveling back again to the left. And eventually it travels through the equilibrium again, and then it starts slowing down, and it stops again. This graph on the left represents this type of a motion. So what should we plot for the velocity as a function of time? It starts from a positive number. The initial velocity is positive, but then it goes to 0. Then it goes to the opposite maximum, and then it goes to 0 again. And when the object travels through the equilibrium again, it reaches maximum to the right. So the graph would look like this. Okay. And it does look like a cosine. And it is a cosine, of course. Now, if we want to write the equation for velocity, the velocity equation, it should have a constant, that maximum speed, times cosine of omega times t. Same period, same omega. In my example on the screen, the period is about 6.3 seconds. And again, to plot the graph for acceleration, it's much easier to use a general relationship between acceleration and the position, because it is always the same relationship. We just have to take a graph for position and multiply by a negative constant. By multiplying the graph on the left by a negative constant, we just have to flip the graph over. It starts from 0, but now it goes down first, 0, up, 0. That's the graph for acceleration. And a similar graph will be for the force, because force is equal to constant, positive constant mass times acceleration. Same period. All right, so a specific problem. 100-gram block attached to a spring with a given spring constant, shifted 10 centimeters to the left from the equilibrium position, and released from rest. So our first choice is between case number 1 or case number 2. We have two special cases. For the special case number 1, we have to use a cosine. For the special case number 2, we have to use a sine. And of course, it depends on how we see the situation. We have to repeat physically what is described verbally. Attached to a spring, moved 10 centimeters to the left, and if my origin is chosen at the equilibrium position, to the left means now it has a negative coordinate. And then we release it. If we release it from rest, it only goes between these two values, negative 10 and positive 10, negative 10 and positive 10. So 10 will be the amplitude. That's it. That's how we think about it. So, of course, picture is worth 1,000 words. The origin, we moved it over here. That's the negative amplitude. So negative 10 centimeters, positive 10 centimeters. We are here, and the initial speed or velocity, call it whatever, is still 0. And when we let it go, it starts moving to the right, reaches maximum speed when it travels through the equilibrium, is always the case. Equilibrium, when it's moving, maximum speed. And then it stops here, Vmax. So when we want to write the motion equation, we have to make several choices. So plus or minus, sine or cosine, and then omega t and nothing else, because two other constants will be set to 0 if we do it right. And equilibrium and origin, same location. So it also helps to look at the graph, to sketch the graph. The graph starts from negative A, goes to 0, goes to a positive A, goes back to 0. That's how the graph looks like, and back to negative A in one period. So plus or minus, clearly a minus. Sine or cosine, clearly cosine. The amplitude, I use meters. How do I make, I don't know, how do I make, oh, it's still like, now it keeps working, okay. So first time it was probably an important person, that's why it stopped working, and now it's not so important person, that's why it still keeps running. Smart. So the amplitude is 10 centimeters, we convert it into meters. And now we need to calculate only one number, omega. Omega equals 2 pi over a period. Can we use it? No. All right, searching for a next connection. Omega squared equals k over m. Can we use it? Yes. So if we cannot use it, we don't use it. If we can, we use it. Spring constant is equal to 10. Mass equals, in kilograms, 0.1. So 10 over 0.1 is 100. But we have to take a square root of that, 10 radians per second. That allows us to complete the motion equation. That's it. Don't answer this question. Scratch it. So let's talk about energy in general. First of all, naturally, we neglect friction, any kind of a friction. In axes, between wheels and the tracks, air friction. If there is no friction, what does it tell us about mechanical energy? We used it before. We still have to use it. The new knowledge doesn't replace the old knowledge. The new knowledge is built on the old knowledge. When there is no friction, mechanical energy is conserved. No matter what is happening, no matter how we made it move. So, kinetic energy changes because it travels faster and slower, slower and faster. But mechanical energy has to be conserved, which means some potential energy should be involved, but not gravitational one. The height is the same. So in this particular case, let's say the object was removed from equilibrium and released from rest. The initial kinetic energy will be 0. But then what is happening to it? Well, kinetic energy equals mv squared over 2. So whatever happening to velocity, we just have to square it. And what is happening to a negative number when it is squared? Becomes positive. So the graph for velocity has two parts. One is negative, it becomes positive. Second is positive, it remains positive. That is the graph for kinetic energy. It changes in time. However, it changes twice faster. The period for kinetic energy equals a half of the period for the position velocity or acceleration of force. So zero kinetic energy, maximum kinetic energy, zero kinetic energy, maximum kinetic energy, zero kinetic energy. That's how it changes. So kinetic energy changes, but total energy shouldn't. So how do we know what kind of potential energy should be used? Well, potential energy comes from work done by a force. And in this situation, there's only one force which does work. It's not normal, it's not gravity, it's not friction because we neglect it. It's elastic force. Only elastic force does work. And the tricky part is the elastic force is force acting from a spring on the object. But it's much easier for us to calculate the force acting on the spring because we just use our hand to stretch it or compress it. According to Newton's third law, those forces opposite to each other. So if we calculate work done by our hand, the work done by spring on the hand will have the same magnitude but just opposite sign. And why is it easier? Because the graph for the applied force looks like this. So positive. How do we calculate work? Well, the work done by constant force is equal to this. And unfortunately, this force is not constant, but we know what to do about it. We can break it, the whole motion into small portions, and for each portion, we can assume the work remains the same, the force remains the same. So we can calculate the work done by the force during the first millimeter, then during the second millimeter, the third, the fourth. And for each small displacement, the amount of work will be equal to the area of this rectangle. Because that's what it is, displacement, tiny displacement, times the actual instantaneous value of the force. So if we add all those individual tiny work together, the result is area. We used this approach to calculate the impulse of a force. Now we can use the same approach to calculate the work done by this elastic force. What kind of shape do you see? Trapezoid. How do we calculate the area of a trapezoid? Well, this will be delta x from x1 to x2. This will be initial force. This will be final force. The area is equal to 1/2 first base plus second base times the height. We just have to look at it like this. Or we have to imagine that we take this picture and turn it by 90 degrees to see a natural trapezoid. Base, long base, height. And then the algebra comes to play, and the algebra tells us that's the result. That is the work done by elastic force acting on this card. It is equal to the difference between two fractions. They look alike. This is the initial location of the card. This is the final location of the card. And now, of course, we give it a name. We call this potential energy of the spring elastic potential energy. And now we can write the law of conservation of mechanical energy. Mechanical energy is equal to kinetic plus potential. The only tricky part about this again. Mass of the spring is equal to 0. It's an ideal spring. It's massless. So kinetic energy here is the kinetic energy of the object attached to the spring for the ball, for example. But potential energy here, and that's people, well, have no agreement yet. They call it potential energy of a spring, which makes sense. You compress spring or stretch spring. You do a work on the spring, and you store some energy in it. But also the same expression people call potential energy for the ball on the spring or system. So this is clear. Kinetic energy, of course, for the object only, but potential energy might have several different names or interpretations. However, the expression is still the same. And if you compare two instances or two locations of the same object attached to the same spring, let's call it initial, let's call it final, we can always write mv initial squared over 2 plus kx initial squared over 2 should be equal to mv final squared over 2 plus kx final squared over 2, assuming the origin is chosen at equilibrium. Otherwise, instead of x, we would have to write delta x. Again, in general, delta x equals actual position minus the location of the equilibrium. But normally, we don't have to think about it. That's the law of conservation of mechanical energy for spring with an object attached to it. So, graphs. We already had a graph for kinetic energy as a function of time. It looked like this. Because kinetic energy is just mv squared over 2. But here we should sketch a graph for kinetic energy as a function of position. So at different locations, kinetic energy is different. Well, this is actually a tricky question. It's much easier to start from potential energy. For potential energy, the equation directly related to x, well, squared. So for the potential energy, the graph is just a parabola. If this is the origin, we go to the left, we go to the right to the origin. The potential energy is quadratic. It doesn't go infinitely up because the motion is limited between the amplitudes. This is the graph for potential energy as a function of position. And now we can apply the law of conservation of mechanical energy. Kinetic energy plus potential energy should be equal to certain constant total energy. So kinetic energy will be equal to that constant total energy minus kx squared over 2. So first of all, the total energy, that maximum amount of energy we can store in the system. What is it equal to? Well, it's reached here at the amplitude, so it will be equal to k amplitude squared divided by 2. So k amplitude squared over 2 minus kx squared over 2. That's going to be a graph which looks like this. When x equals a, no kinetic energy. When x equals negative a, no kinetic energy. Kinetic energy reaches maximum at the equilibrium when x equals 0. Which makes sense. travels like this. Fastest motion happening at equilibrium, maximum kinetic energy. It stops on one side, it stops on another side, zero energy. So this is how the graph for kinetic energy as a function of position looks like. Now, final question, since we're on energies, how would the graph for potential energy as a function of time look like? All right. We start from x. Well, actually, let's make it red. So the equation, the graph should work for any case. So if we consider the easiest case, case number 1 starts from rest, away from equilibrium. Potential energy is equal to kx squared. So we just have to square the graph for the x. And what do we do to do that? Well, positive numbers remain positive, but negative numbers become positive. So this blue line represents how potential energy changes in time. And we can see again that it changes twice faster than coordinate. So the period for the potential energy is equal to a half of the period of the motion, exactly like the period for kinetic energy. A half of the period of the motion. Well, mathematically, it's because we square things. So we don't have negative parts anymore. Everything becomes positive. So these are nicer representations of what I just said. And this is a neat mathematical example of conservation of mechanical energy. So if this is how we can calculate potential energy, and this is how we can calculate kinetic energy, if we add them up, there is a trigonometrical identity which says sine squared plus cosine squared equals 1. That's basically a Pythagorean theorem. So if you add them up all together, you get that the sum will be always constant. And that constant has been found already. It is equal to maximum potential energy, but also, you see what is happening to energy? Kinetic decreases, potential increases. Kinetic increases, potential decreases, but the sum remains constant. So at the maximum displacement from equilibrium, it stops. No kinetic. All energy is potential, Ka squared over 2. When it travels through equilibrium, no potential. All energy is stored in kinetic, m v max squared over 2. That is it. All right. Thank you very much. Please pick up your exams if you haven't done it yet.